looking let's look at how we define weather and climate. I think everybody has an intuitive sense, but let's go through it anyway. So here is a temperature record from some place on Earth, which is showing something like hourly or weekly temperature or some sort. You can see some high frequency variability there going from 1995 to 2013 or so, and you can see some cycles in there which are the annual cycles, and there is some seasonality within it and so on. And this is for 1 year. So what is weather? Basically, it is what changes every day. If the sun goes up and sun goes down, except in the polar latitudes, and if sun goes north and south with the seasons, then you have two dominant time scales of solar radiation forcing. And yet, depending on where you are, weather can change several times a day. This is the internal feedbacks that we talked about: evaporation, cloud formation, rain, storms coming through, and so on and so forth, right? In the tropics, you don't have very well defined seasons, but you can still have something like a monsoon season, for example, deep in the tropics, and so on. So weather today, as I'm recording this, is 5th of November. In India, the summer monsoon has ended. Winter is not here yet. Winds are changing from southwest to northeast, so it's a little bit less humid, and no rain expected at all, mostly clear skies with some high clouds. So on November 5th, you would expect the weather to be drier and cooler than, let's say, August 5th, because you expect August to be climatologically a rainy month, hot, humid, rainy, and November to be, at least in Mumbai, drier and sunnier, and no rain, right? So this is what climate would tell you. But weather means on a given day in August, it may just happen that you are in a monsoon break period. Winds are coming down from above, so it's drier and maybe even cooler because it's heavily raining somewhere away from Mumbai and pulling down some air. Not really possible in August, but nonetheless. So weather on August can end up being cooler and drier than November 5th. So weather is what we get, and climate is what we expect. This was attributed to Mark Twain, but apparently a lot of people do research and say that's not who said that first, and so on and so forth. What is climatology? So we take, let's say, every week of the year in every year. So first week of January for about 30 years, and make the mean January first week, and then the second week, third week, and so on. So this kind of scale, time scale derived here, it's showing January, February, all the way up to or January and May, August and December, and you can clearly see a seasonal cycle here. Warm in the summer, cool in the fall, winter months, and by spring, by fall, it's getting warmer again. So this is like a rainy season, which tends to be cloudy and cooler than the pre-monsoon months, and so on. So climatology is the long-term average. There is no strict definition of what is the long-term average, but typically we take 30 years, but depends. Okay. So what is climate change then? So if you look at temperatures from particular places like Chennai, Mumbai, Delhi, and Bengaluru for more than 100 years, here 1882 to 2014, you see that there are year-to-year variabilities, but there is also a increase in temperature from here in Chennai 27.9 as an annual average to 28.8 and so on. Each of these places is showing some increase over this time period. So the increase over some time, again not strictly defined, is called climate change. Okay, obviously if it just happens in 10 years, we call it decadal change rather than climate change. So the trends have to be on sufficiently long periods, let's say a century. You can also think of shorter periods as secular trends, for example 20, 30 years and so on. Okay, so climate change is not that well defined, but nonetheless you intuitively know what that means. As for paleoclimate, we have reconstructed temperature records not as absolute values, so these are measured absolute values, whereas these are derived anomalies from some base period. Let's say we use a base period of modern times like 1960 to 1990, and we compute the deviations from this climatology, not always seasonal cycle but maybe yearly or decadal variability, and you can see the times resolution of these records changes. Seems very smooth here over millions of years, whereas here it's got much more wiggles, and there are different lower frequencies as well. So climate has changed over a large range over these last 65 million years or so, and there are some strong spikes like the Paleocene-Eocene thermal maximum, which occurred over a few thousand years, so it's still much slower than the warming rates we are having now since the Industrial Revolution. And you can also see other features that we are kind of in a cooling trend over the last 50 million years or so. What are the reasons? We'll look at it just a little bit. The time scales of these wiggles also change. We have more wiggles here than here, as I said. So there are various proxies, which means they don't measure temperature directly, but temperature changes can be inferred by looking at chemical signatures like the oxygen isotopes in certain phytoplankton that live in the ocean and so on, or from an ice core where the gas molecules are trapped and so on and so forth. So we'll see what are the paleoproxies are, at least a few examples. And remember that the climate changes all the time, but now we have to see what we are doing and at what time scale we are doing these. There are asymmetries as well. This is from the Vostok ice core, which is now extended to almost 800,000 years and beyond, and it is showing CO2, methane and temperature. And for good measure, it has added the changes in methane, CO2 and temperature since the Industrial Revolution, and you can see that we have increased the CO2 beyond anything we have seen in the last at least a million years, and methane is also increased quite a bit. You have to be careful here, the units are different. This is in parts per million by volume, and this is in parts per billion by volume. We'll come back to that. And you will see that the temperature has not increased corresponding to that. We will see why that is. And we'll also talk about the asymmetry. So there is a cooling here. So decreasing CO2 and methane and cooling temperatures are occurring on a longer period than these apparently abrupt warming. So there's an asymmetry and a sawtooth structure in this, and we'll see why that is. Those are what we mean by feedback. So the forcing is coming in at some time scale, but the Earth system with land, atmosphere, ocean, glaciers and so on is creating its own time scales because of these internal feedbacks. Okay, those feedbacks are the critical things we must understand, especially for projecting into the future.